for the moment. I got my old program Doceri to work again, so I'm going to try it. If you like the old way I did it this morning better, let me know, and I'll keep doing it like that. But this PowerPoint, we're going to talk about binding energy. And binding energy is, for me, particularly of interest. I did a college paper years ago on binding energy and what it has to do with the bombs that were dropped on Japan to end the war. And also, one of my favorite all-time scientists is Albert Einstein, and it was he that came up with the whole concept of binding energy and mass defect and those things that we're going to talk about today. So it is of particular interest to me. But let's talk about what it is. Binding energy does come from the neutrons, and we have talked about that it is their job to hold the protons in place, and that it's certainly not an easy job because, keep in mind, very, very dense. Those protons don't want to stay together because they all have these positive charges and they want to get out. So for the lighter elements, on up to about calcium or thereabouts, for every one proton there's one neutron to hold it in the nucleus. But when you get up heavier than about calcium, it takes more neutrons to hold the nucleus together. Those neutrons, their job is to keep the protons in the nucleus and held in. So we also talked about that word nucleons. This word right here, nucleons, is the sum of the protons and neutrons together, their masses, that make up what's called nucleons. If you were to add up the mass of all the protons plus all the neutrons in the nucleus, and we were to weigh them, if we somehow had a scale that was small enough to weigh them, and we said, okay, this is what their mass should be, and then we were to actually weigh them, they wouldn't be the same. They wouldn't be the same. And the difference between those is called mass defect. And what it was determined was that the difference where that energy came from is called is converted into pure energy that is used to hold the nucleus together. And if something happens to release that energy, my goodness, what an amount of energy that is released. And it is released according to Albert Einstein's very famous equation, E equals mc squared. So let's look at how to compute the amount of energy. For example, here is the actual mass. This is an example that's in your text. Here's the mass of an isotope of fluorine. It has this actual mass, but let's add up what it should be. If you have 9 protons and 10 neutrons, 9 protons comes from there, and then you subtract these and you get, there's 10 neutrons, so there you go. So let's find out what the mass should be. Well, the mass of a proton, and you would be given this, there's the mass of a proton right there. So if you take 9 times that 1.0078, well, that's equal to 9.074185. And then here's the mass of a neutron. Slightly more. Remember, I told you that a neutron is actually comprised of a proton plus an electron together, and then a little gluon that holds them together. So then if you had 10 times that 1.0078, you're just going to move that decimal. 1.008665. Well, that equals 110.08665 AMU. So if you add those two numbers together, the 10.8665 plus the 9. If you were to add those two numbers together, then that gives you what the mass of the nucleus should be. and you're going to see that this mass actually should be, let me get my calculator out. It should be 19.157075 AMU. But here's the actual mass right here, 18.99. The difference between those two is called the mass defect. The difference between what it should be and what it actually is, that, where did I go? That 19.15705, that's what I got. She got 7 more weight, minus the 18.99840, I'll use her number there, is 0.15868, and it's actually negative because this is how much it actually is, and this is what it actually should be, so it actually is negative. This is called the mass defect. That's the difference between what it actually is and what it should be. Okay? Where does that mass go? That mass gets converted into energy. So when it's formed, it's actually exothermic or giving off heat. That's binding energy. And we can actually calculate that using Einstein's. You've seen the signs all over the place all the time. E equals mc squared equals mc squared. Well, what do they really mean? E equals mc squared. Well, this right here, this delta M right here, or in this case you put a delta M, change in mass. This E stands for energy, so the amount of energy given off or taken in is equal to the change in mass, so the mass that it should be compared to the mass that it actually is, or the mass defect, and then this C stands for the speed of light squared. So we could calculate how much energy is going to be given off or liberated, if you would rather use the bigger word there, by taking our calculations. So we're going to take our mass defect right here, and since this is in AMU and mass is measured in kilograms, we're going to change our AMU, use some dimensional analysis to change this tiny AMU into kilograms. So this is how much it is in kilograms. That's all that's being done right there, is it's being converted over into kilograms. And then we're going to sub it into our formula, is E equals mc squared, where C is the speed of light. I would personally not have used the 2.999. I would use 3.0 times 10 to the 8. That's what's accepted in physics. So we could say that the energy given off is equal to the mass defect, the change in mass rather, times the speed of light squared. The change in mass times the speed of light squared. So our mass defect was that negative 2.6 times 10 to the negative 28 kilojoules, or kilograms rather, and then the speed of light is 3.0 times 10 to the 8th, and you have to square that. E equals mc squared, so you're going to square that. So each atom that's formed is going to give off this many joules of energy. Now that doesn't sound like a lot. However, think about how tiny a single atom is. And if you have a mole of atoms, then that's a significant amount of energy indeed. Okay? So if you multiply that times a mole, then That's a lot. You can see here in this that this is what the answer was. Not very, doesn't sound like very much, but now change that into moles. 6.02 times 10 to the 23rd particles in 1 mole, and now you have a significant amount of energy in a mole. And then change it into kilojoules instead of just joules. So that is a very significant amount of energy that's given off in a mole of fluorine atoms just to hold the nucleus together. Now if you multiply that times how many, in the case of the bomb being dropped on Japan, how many moles of uranium in this case were dropped in the bombs on Japan, that equals a huge amount of energy that's being released. So let's talk about that. When comparing the stability of this, then it makes sense to talk about it per however many nucleons you have, that is, however many protons or neutrons that you have. And so that's what she's talking about here. But to me, it's still an enormous amount of energy. Okay, so this is what she's talking about right here. When you compare the stability of any two nuclei, you need to talk about the fact that they have different numbers of nucleons. That is, remember what a nucleon is. It's either a proton or a neutron. So it makes sense that you want to compare each nuclei by comparing their numbers of nucleons. So for the fluorine atom that we've been talking about, each simple proton or neutron gives off that much energy, 1.2 times 10 to the negative 12 joules per proton or per neutron. And then this is what you can see from that. The greater the nuclear binding energy per nucleon, the more stable is the nucleus. So the larger this number is right here, the larger this number is right here, the more stable your nucleus is. And that kind of should make sense to you too. The harder it's going to be to break that apart. Okay, and you can see that this chart here that's also in your textbook, that the highest binding energies are going to be those elements between 40 and 100. Those that are in the right smack in the kind of the middle of the table. Starting zirconium, lead, those are the most stable, then the hardest ones that are going to be the most stable as far as radioactivity goes, stability. Okay, and so if you were to do the sample problem that's in your textbook in section 20.2, you do it the exact same way. Calculate the binding energy of this nucleus and then per nucleon. So all you're going to do there is we're going to do this exactly the same way. Work this out super quick. You have to calculate how many protons. We have 53 protons. And we're going to subtract. That's a 4 and that's a 7. And so we have 74 neutrons. And remember from the page before that each of these neutrons has a mass of 1.008665 AMU. And each of these protons is 1.007. Oh, I can't remember. I'm going to have to go to the next page to remind myself. 1.007825. That's what it is. So it was 50. So it's going to be 53 times the 1.007825, and that's the mass that the protons should have. Okay? Individually, that's... And then, since we have 74 neutrons, That's their mass of a neutron. And so multiply that. And so that's what the mass according to the number of neutrons that there should be. You add these two numbers together, and this is what the mass of the atom that it should be. The nucleus should be 128.05594. That's what it should be. The actual mass that's given to us in the problem was actually 128. This was the actual mass that was given to us in the problem, 128. I'm sorry, this was what it should be, based on our calculations of how many protons and how many neutrons. That's what it should be. This was what was given to us in the problem, in the sample problem, 126.904473 AMU. So if we subtract these two numbers, we're going to get a difference of negative 1.5147. Now, here's the, I will never ask you to know this, I will give it to you every time. Here's the conversion to change from AMU to kilograms. So this is how many kilograms it is. It's tiny. But we're talking about the mass of a single atom here. Actually, a single nucleus. So 1.9126206 times 10 to the negative 27th kilograms. That's how much there is the difference between the mass that it is and the actual mass that it should be. Alright, then according to Einstein's E equals mc squared, there's our mass in kilograms. Here's the speed of light, and you have to square it. So 3.0 times 10 to the 8th squared times this mass, and we get this. Kilogram meter squared per second squared, which is a joule. So this is how many joules for a single atom, per atom. But the question, so this is part one. Okay, so this is the binding energy for this. But it asked you for the second part to also do it per nucleon. So we'd have to go back to what is our mass number. Well, the element was 127 over 53. I believe it was 53. And so iodine. And so this asked us per nucleon. Well, a nucleon can be a proton or a neutron. So we're going to take this answer that we got and divide it by 127. So then you get this, joules per nucleon. Now, I would probably stop at how many joules per atom, but you should be able to do both because it's just one more division. And it looks daunting, but each step is not difficult. Okay? And then the other kind of thing that we're going to do is radioactive decay, but I'm going to put that on a different PowerPoint.